eccentricity, ellipse, and hyperbola. I should have spoken about this topic early on in the topic of ellipses, but since it so happens that we also have this thing called eccentricity of a hyperbola, so I think it is still fitting to talk about the eccentricity of ellipse and hyperbola. Eccentricity of an ellipse. So given the absolute distance A of the vertex from the center and the absolute distance of C of the focus from the center, the eccentricity E is computed in the following way. E is equal to C divided by A. Now these are the properties of your eccentricity for an ellipse. For an ellipse, the value of E is between 0 and 1. Okay? Now, why is that so? Why is that so? In this ellipse, for example, okay, x squared over 4 plus y squared over 9 is equal to 1. A squared is equal to 9. So that means A is equal to plus or minus 3. So one vertex is 3 units above the center. And the center here is the origin, okay? And so that is one vertex. And the other vertex will be 3 units below the center. The focus is between the center and the vertex, which is why C is always less than A. And if C is less than A, then C over A is going to be between 0 and 1, or it is less than 1, okay? Now, when E approaches 0, the ellipse is close to being a circle, okay? When E is close to 0 or is approaching 0, the shape of your ellipse is resembling the shape of a circle. Now, why is that? Why is that? Well, pay attention to the value of C squared. So C squared is equal to A squared minus B squared. And so when C or C squared approaches 0, this means A squared minus B squared is equal to 0, or it is approaching 0, and which means A is almost equal to B. Okay? And so this also means that the major axis, okay, this is your major axis, okay, is almost equal to the length of your minor axis, in which case, what you will produce is a set of points that is close to the circle. Now, another way of looking at it is when E approaches 0, C, the distance of the focus from the center, approaches 0, in which case it's telling you that the center and the focus are close to coinciding with each other. Okay? And so the fixed point now becomes the center, so to speak. And you know what sort of set of points is a set of points that is equidistant from the center. You know that to be the circle. And so here, the eccentricity of this ellipse is going to be, okay, greater than the eccentricity of this ellipse. This one is close to 0. Now, the reason why I cannot skip this topic is because it reveals a lot about the orbits of the planets and other space objects in the solar system. So the orbit of the planets around the sun and the orbits of other space objects around the sun, they are in the shape of an ellipse, but they have differing eccentricities. Now look at the orbit of Mercury. So the orbit of Mercury is an ellipse whose eccentricity is 0.206. Now compare that with the orbit of Venus. Venus is the blue orbit. So between Venus's and Mercury's orbit, Venus's orbit is almost like in the shape of a circle. The same with Earth. Earth's orbit is 0.017. Okay? And so those things are telling you something. So the orbit of Earth around the Sun is almost like in the shape of a circle. Now pay attention to these two other space objects, the Icarus. Icarus is an asteroid. So in the solar system, we have a region in the solar system, Kuiper Belt for example, that is occupied by many asteroids and many space objects. You call that the Kuiper Belt. And Halley's Comet is another space object that orbits around the Sun. So it's like the Sun is one of its foci. And look at the eccentricity of Halley's orbit. It's 0.968. So it is really an exaggerated ellipse. Okay, it is an ellipse whose shape is distinctly that of an ellipse. We also have the eccentricity of a hyperbola. So given the absolute distance of A of the vertex from the center and the absolute distance C of the focus from the center, we compute E in the following way. It's also equal to C over A. But in this case, E is always greater than 1. And these are the other properties. Now, why is that so? Well, because C or C squared is always greater than A squared. Okay, look at that. And so when you get the ratio of C to A, it's always going to be greater than 1. Now, what happens when E, the eccentricity of a hyperbola, gets close to 1? And by the way, those two intersecting lines there, the broken lines, they are the oblique asymptotes. So the branches of your hyperbola follows the direction of your oblique asymptotes as x approaches infinity. Now, when E approaches 1, the oblique asymptotes make an angle that is narrower. Or in particular, the latus rectum. Okay, so the latus rectum is giving you the focal width of the branches of your hyperbola. And so when E approaches 1, the latus rectum becomes shorter. Okay, something like this happens in that situation. Now look at this. Here, B squared is equal to 4. Okay? Now, when B squared gets closer to 0, C squared gets closer to A squared, in which case our ratio C over A approaches 1. Okay, here we have a value of B squared which is equal to 0.5. And so the result of that is to shorten your latus rectum, and it will produce a hyperbola whose focal width are narrower.